In this video, we see that not all functions have inverse functions. This is a perfectly reasonable function. If I feed any x value into this function, I will get out specifically one value for f of x. If I feed in x equals 1, I'll get 0 squared plus 1. If I feed in x equals 101, I'll get 100 squared plus 1. There's no problems here with any possible x value that I feed in. I'll know exactly what I get out. But there is a little bit of funny business going on here. In particular, consider this. If I feed 2 into f, I get 1 squared plus 1, which is 2. And if I feed 0 into f, I get negative 1 squared plus 1, which is also 2. So if I try to write an inverse function, and I ask, what is f inverse of 2, what should I say? I see here that if I get an output of 2, it could have come from 2 or from 0. In this case, we say f does not have an inverse function. We could try doing what we did last time. Here is essentially how f behaves. It turns x into x minus 1. Then it squares that. And finally, it adds 1 to that. If I tried to work backwards here, from here to here, we added 1. So from here to here, I'll subtract 1. And from here to here, we squared what we had. So from here to here, I'll undo that. And here's where the problem comes in. If I have a minus 1 here, how do I know what was here? Is it the positive square root of a minus 1 or the negative square root of a minus 1? In some sense, I could continue like this. I can split a minus 1 into either the positive square root or the negative square root. And now I just need to undo this last or first, depending on your perspective, step. From here to here, I subtracted 1, so from here to here, I'll add 1. And let's check that this works as we'd like it to. If I start with an a value here of 2, and I run through these steps, I hope that one of these tracks will get me to 2, and the other one will get me to 0. Let's see what happens if I plug in a equals 2 and run this track. I'll get 1 plus the square root of 1. In other words, I'll get 1 plus 1, I'll get 2. And if I run this track, I'll get 1 minus the square root of 1, I'll get 0. But notice here that when I feed a specific a value into this inverse process, I don't get one and only one output. And if I don't get one and only one output, then what we're looking at does not deserve the name function. So in some sense, I do have a way to invert this equation, this process, but I certainly don't have a nicely defined inverse function. We could also see this idea visually. If I look at the graph of this function, it looks something like this. How do I think of this inverse function in this picture? Well, what I'm thinking is if I choose some output, in other words, I say, look at this particular y value, and I ask, what x value is associated with this y value? Well, I can see quite clearly that there's one x value over here that's associated with this y value, and another x value over here that's associated with this y value. So when I plug this y value in and ask what f inverse returns, I get two possible values. So if I wanted to tweak this function so that it did have a nicely defined inverse function, I could restrict the domain. In particular, I could say, I want to consider this function, but only over here, and scratch off this bit. Now, if you specify any particular y value, I can tell you exactly the associated x value. Essentially, by scratching off this bit of the graph, we'll also scratch off this bit. And now we do have a nicely defined inverse function. Although it's worth pointing out that this inverse function is not defined for any choice of a. If I specified that I was looking for the x value which was associated with this y value, I wouldn't find anything. So how can I see that? Well, if you look at what's going on here, this square root of a minus 1 is really only going to make sense if a is greater than or equal to 1. So I could specify my inverse function here. After restricting this domain, I could say that f inverse has this rule with this domain.